Hello and welcome to today's webinar. My name is David Cash. I'm a member of the marketing team here at Mountz, and I'm glad that you have taken the time to join us for our first webinar of 2026 as we look at our topic of how to select an electric screwdriver for precision assembly. Now, there are a lot of different types of electronic torque screwdrivers, and that's primarily why we're doing this webinar today. But with those different types of screwdrivers, they are designed to help mitigate against different types of fastening risks that may be associated with the actual assembly. And obviously, we want tools that are going to provide us the proper torque because if a fastener is over torqued, then it can put too much stress on that fastener. If there is too much clamp force for that particular specification, and any type of shock or vibration can cause that fastener to fail. The converse of that is if the torque is under torqued, that would then cause any type of vibration or shock to cause that fastener to possibly back out. Again, not keeping the components together that we would like, and we would see failure that way. There's also the human element that is involved, obviously, in a lot of the fastening that is done. And so things that we can help to mitigate from the actual process by using the correct screwdriver is going to help us eliminate and reduce some of those fastening risks that are associated with the assembly. Now, when we're talking about using a torque screwdriver, or electric torque screwdriver in this case, you may hear the actual term of static torque versus dynamic torque. And basically what that means is a dynamic type of torque tool is one that is generating an RPM, and a static tool is that would be used typically as a hand tool, maybe a torque screwdriver or a torque wrench. And so a dynamic torque tool is again going to be generating an RPM, and that RPM can affect the torque output, and we'll talk a little bit about that later in the presentation. You also may hear this as it relates to torque testing. So a static torque sensor would be a reaction style transducer, and then a dynamic transducer allows us to be able to test a power tool in its dynamic state. So that may come up as well. Now, why would we want to use an electronic torque screwdriver? Well, you may be moving from a situation where you are using a hand tool, a torque screwdriver, and you want to help speed up production a little bit. There may be health issues as it relates to the amount of turning or twisting an operator may be doing with the use of a hand tool. And so we want to move to a power tool that's going to allow the operator to help reduce any type of carpal tunnel or repetitive motion injury. You may also be moving from an air tool to a electronic tool, and that could be because you want to reduce the amount of particulate that may be generated by the exhaust of an air tool. There also may be hearing or decibels that are created by the use of an air tool that aren't for an electric tool. So there are some reasons why we would want to use an electronic screwdriver. Now, they are limited in the amount of range that a standard electric tool can produce. And that's typically from a very low inch ounces up to about 80 to 90 inch pounds, depending on the model that you may be looking at. So those would be some of the limitations, especially if you're moving from an air tool where those can produce a much higher torque value. So what are some of the factors that we may be looking at when we are considering using a electric screwdriver? And the first one is going to be the material that is being used. And so if you have a self-tapping type of application where you may be running into plastics, some of the things to consider there are going to be the thread pitch, the material density that may be used, the RPM that is going to be used during that operation. So material is one thing that we want to consider. Next is going to be the amount of fastening that's going to be done. Is it going to be a high volume type of application or a lower volume application? And we'll talk a little bit about which type of tool is going to be best for each of those scenarios. Next, we're going to look at the RPM. So will we be able, do we need a really high RPM tool? How that is going to affect the actual torque output that's being generated? And do we need some type of variable RPM that we can adjust to make certain increments work better for a particular application? And then next is the application itself. Does it need to be ESD? So if we're doing any type of fastening for electrical components, and those, we want to make sure that the driver that we're using is an ESD approved for that, or compliant for that particular type of application. So that is another consideration. And then finally, the fastening joint that is actually being used. Is that a hard joint or a soft joint? And so there are different joint classifications, hard and soft. There could be medium as well, but typically we're looking at a hard joint is going to have anywhere up to 30 degrees of rotation. Once the fastener gets seated and the bearing surfaces mate, the fastener itself is going to turn less than 30 degrees. And then a soft joint would be once the bearing surfaces mate, it rotates for at least 2 revolutions or up to 2 revolutions in that 720 degrees would be considered a soft joint. And the reason that this is important is because a softer type of joint is going to require more load on the tool. So we want to make sure that we have a robust tool to be able to compensate for the additional load that may be generated during that rundown process of hitting that 720 degrees in there. So variables that can affect the torque, we've touched on it a little bit, but primarily we're going to be looking at the biggest one is going to be lubrication. If there is going to be a thread locker attached or placed on a fastener, is that going to give us a lower coefficient of friction that we're not compensating for, causing an extra stretch in the fastener? Are we going to be using any type of fastening pitch, or excuse me, a thread patch in there that's going to be changing the amount of prevailing torque that is in there? Another consideration is going to be, again, the RPM speed. Typically, when we look at a really high RPM tool at a very low torque value, the amount of inertia that is generated from that tool when it shuts off can add additional torque to the fastening and cause some of those readings to be a little inaccurate. So if we're dealing with a low torque value, we want to make sure that we are dealing with the correct RPM that is not going to be affecting the torque output. So those are some of the variables. Again, the human element is one of those things, and anytime we can error proof that, that is also helpful. But that is a discussion for a different webinar as well. So that's going to move us to our poll question for today. Okay. Let's see. All right. Okay, so the poll is how to select what type of electric driver are you using currently? A lever to start, push to start, robotic driver, or a cordless driver? So we'll give you just another couple seconds here to respond. Awesome. It looks like the push to start is the overall winner. And thank you very much for participating in that. So there are different types of screwdrivers, electronic torque screwdrivers, for different purposes. So let's go through some of those and highlight what those differences are. So the first one that we're going to look at is going to be a direct plug-in style of tool. Now this basically means that the power cord comes from the tool and plugs directly into the outlet. Now with this, there is a transformer, but it's built inside of the tool. So this type of tool is designed for a very low volume type of application with a very low duty cycle, meaning that if we run the driver down for 1 second, it needs to rest or cool down for at least 3 seconds so we don't burn up the transformer that is inside the tool. So if you were to take a direct plug-in style of tool and use that in a very high volume type of application, that transformer is going to get overheated and eventually fail because of the fact that the transformer is built inside the tool. So if your application requires a few fastening here, a few fastening there, with time for the tool to rest and cool before its next operation, this would be a good style of tool. The other advantage to the direct plug-in style of tool is that it is typically more cost-effective, less expensive than the next tool that we'll talk about, which is going to be a transformer style of tool. And so this basically allows us to have a very high volume type of application with a very quick duty cycle that allows us to be able to use the tool in rapid succession, one after another, and the transformer is outside of the tool. Now, with the use of the transformer style tool, that can give us different types of output from that tool. So it could be the ability to have a lower RPM or a higher RPM. Sometimes there is a switch on the transformer that allows for that. There may be some additional inputs or outputs that we can use from that tool that can be controlled through the transformer. So if we are doing any type of line control where we want to lock the tool or allow the tool to be used, we can do that through the inputs and outputs of the transformer style of tool. With that also comes the ability to have a tool that can be programmed to run at different RPMs. And so we can set this tool up for one application that may run at a specific RPM. Then if we wanted to move this tool to another operation at another time, we could then program this tool to run down at a slower RPM. And so different styles, or excuse me, different ranges of tools have different increments of variability RPM. So it just depends on the model and the range. But this can be very useful and very helpful in being able to spec the right RPM for a particular application. Next is going to be a screwdriver that can allow you to have a soft start to the operation. And this is really helpful if you have the instances where an operator may be using or causing cross-thread type of an event. So you may have a really fine threaded type of fastener, and that may be giving us a lot of issues as it relates to cross-threading. So a soft start tool allows the tool to ramp up to its RPM speed giving us more control at the very beginning of the rundown. Now, at the end of the rundown, we also have the ability to have a soft stop. And this is for those types of tools, or excuse me, those types of applications that may be very delicate and sensitive to shock or vibration. So if we're dealing with any type of soft plastics or ceramics or boards, things like that, that may be damaged by any type of hard shock or something, we do have soft stop versions available as well. We also have the ability to have a push to start, which is a very popular type of tool. And you often see this type of tool being requested when you have operators that are used to using an air tool, because a lot of air tools are a push to start operation. Now, the difference obviously between a push to start and a lever to start, some things that can be problematic with the push to start is that if the operator is not fully engaged on the fastener and pushes down and the bit is not engaged, it may jump off the fastener and could damage the part. You may obviously can have situations where the operator may not be intending to start the tool. There have been cases where an operator is hurt because they accidentally pushed down on it and the bit actually injured them in their hand. So a lever to start would help to mitigate that, to make sure that the operator is actually on the part. But a lot of operators do like the push to start, so that is an option to use as well. Next, we're going to talk about the different types of motors. There are brush and brushless motors, and it's pretty simple there. In the brush motor, we are using carbon brushes to help power the electric motor, and the brushless motor, there are no brushes. And so I'm sure everyone is probably familiar with how this works, but we do have an electrified circuit that is causing the magnetic poles to allow the motor to rotate. And those carbon brushes are pushing in on a commutator to make sure that that circuit is happening. And as that motor spins, those brushes will eventually wear. And so here's an example of what that is. So we have pressure on the commutator there with the brushes, and as the brush motor spins, those carbon brushes will eventually wear out, and so there needs to be maintenance done to change those. It also may create some particulate in there as well. But with a brushless style motor, those brushes are removed, and the internal operations of that motor allow it to rotate the output shaft without the use of the brushes. The push and pull happens all electronically, and that allows the output shaft to spin. Now, when we look at the difference, what may happen with the particulate that's generated from those brushes, you can see here that on the left we have a inside of a tool that uses a carbon brush, and then versus a brushless tool. So depending on the level of cleanliness that you may need in an operation, you would want to choose one that may fit your particular application. The advantage for the brushless tool is no particulate. However, the advantage for the brush tool is that it's typically less expensive than a brushless motor, but you do have some maintenance that is required for those particular types of tools. Now, there's also clean room types of screwdrivers, and in this scenario, you can see that we have a vacuum system that is attached to the port where the brushes are, and that is pulling the particulate away from that. So screwdrivers can be used in a clean room environment. especially brushless, which would be more conducive for that particular environment. But if you do have a brush motor system, you can use that adapter with the vacuum system for that. And then on this one, and also our next example here, is you can also use a vacuum pickup for that particular application. And basically, the vacuum pickup allows you or allows the operator to move the tool, pick up the fastener either from a presenter, a screw presenter, or a shaker tray, grab that fastener right on the tip of the tool and go ahead and do the fastening. So the operator does not have to pick up the fastener or anything like that. The vacuum pickup will do that for them. There's also robotic styles of tools. These can be attached obviously to a robot or a cobot. And those would be more of an automated type of electronic screwdriver. And then we also have cordless types of tools. Now, the cordless screwdriver typically is a pistol grip style of tool. This is our EPT product, and it is available in a pistol grip or a right angle. Sometimes you may see offerings that will have an inline version. Typically, they don't go too high in torque, though, because if they go too high in torque, that can cause that tool to spin in the operator's hand, causing a dangerous type of situation. But these types of tools are available as well. And then finally, we have DC control type of tools. These are programmable styles of tools that give you the ability to have multiple different presets that can be used to create different fastening profiles for different assemblies within one fastening process. And these really give you the most control and a lot of variability to be able to meet different types of application requirements for different joint classifications, all within the use of one tool throughout the range of that tool. Now, if you're interested in DC tools, we do have a lot of different webinars that are dedicated to just the DC tool, but if you're not familiar with those, they do give you a lot of flexibility, a lot of control, and the ability to document what is actually happening during the rundown. Some of the accessories that you may see with an electronic screwdriver are going to be the use of a pistol grip attachment. So you can turn an inline tool into a pistol grip style of tool. We also have a right angle attachment. So you can put that on the nose of the tool and convert that from an inline tool to a right angle tool. Now, you would need to do some testing to make sure that the output is what you need for the use of that tool, because there may be some frictional loss in the gearing for that. So that is one thing to consider. We also have tool balancers to make sure that the tools don't accidentally get dropped or damaged. And there are different styles of tool balancers as well. We also have screw presenters. These are going to help, again, give the ability for the operator to quickly pick up a fastener and put those into the assembly. Next, we have a torque arm. So anytime you go above typically 20 to 15 to 20 inch-pounds or so, you may want to consider putting that tool in a torque arm. This helps to prevent the operator from getting any type of carpal tunnel type of injury or repetitive motion injury, and helps keep the tool secure, giving you 100% transfer of torque from the tool to your part. And there are many different styles and different application uses of the different styles of torque arms that are available as well. We have nose cones that go around the nose of the tool where the torque adjustment happens. And so This helps to prevent the operators from accidentally changing a torque value or accidentally on purpose changing a torque value. So this helps to keep that secure. And then finally, we have the ability to add a screw counter, again, helping to error-proof an assembly process, giving us the ability to monitor a particular application, making sure that all of the fastening gets done and gets done correctly. The different torque screwdrivers. So that down adapter on here, and basically the rundown adapter allows you to be able to simulate the tool at its running RPM. Now, if we were to just stick the rundown adapter into the transducer, turn it on, it's going to immediately clutch out, and it's going to produce a value, but that value is going to be different than if we were to go ahead and let that tool, run to its RPM. So we have a rundown adapter, and it's very similar to our other analyzers, but because we're dealing with such a small torque value, we have just introduced the 1 inch-pound analyzer. This is our 3 inch-pound analyzer, and we also have a 5 to go with the rest of our models. But this would be a 50 inch-pound transducer to go into either our reaction style transducers or our LTT product as well. But just to let you know, this is our soft joint rundown adapter here. And I've got a couple different screwdrivers here, but this would be one driver that we have. And you can see here that this is a brush style tool. It's because we have our brush ports here. If we go ahead and open this out, we can pull out those brushes and replace those if needed. And then this would be a brushless style version. Again, there's no ports for the brushes. This one also gives us the ability to set the RPM and be able to initiate the soft start if we like. But these particular drivers are controlled by a clutch mechanism that is allows us to change the torque by how much tension is placed on to a torque spring. Now, you may see one tool may have 2 different springs, or could be maybe even 3 different springs, but they're usually colored springs that will produce a different rate of torque. So if you do that or have to change it, you can go ahead and do that. But this gives us the ability to have one tool that can reach different torque values with different springs. And there are also little reference marks that are available here on the inside of the tool that will allow you to set this cone to a certain value here. And so that is, again, just a reference point. It's not an actual torque value. And then if you get it set correctly, you can go ahead and put down, there's a little set screw here, or you can put your torque cover in here. There's threads in here. We can go ahead and put that torque cover on there. So if we want to go ahead and use a torque analyzer to go ahead and set our tool, I have one of our drivers here. We can go ahead and run this down and see what we're getting. Go ahead and let it warm up here. Okay, if, for example, we want to go ahead and try and set this tool to, say, 1.5 inch-pounds, we'll go ahead and change our target torque here to 1.5. And come back to our operation screen. This now gives us that target is at 1.5. If I go ahead and run this down, you can see we're at about 1.3, 1.4-ish. So I can go ahead and I can turn the cone here a couple of clicks, and this is going to allow us to increase the actual torque value. So you can see I've gone a little bit over, so no problem. We can come in and we can back that off a little bit. And there we're kind of dialing it in better to where we want this tool to be. And if we go through the actual process here, set our tool, then we can go ahead and put that tool out in use. But that's how the tools function with that clutch mechanism, the spring in it, and then also how you would set it up on a torque analyzer as well. So that's going to bring us to the end of today's presentation. That's going to lead us into our questions and answers. So let's see, Chris, do we have any questions?
Hey Dave, one question we had is, what's the difference between the tool's accuracy and repeatability?
So the repeatability is going to be a grouping of readings that are really close to each other. And then accuracy is going to be how close that group of readings are to the target. So on average, you could have a very accurate tool, but the points are making up for it by the average because they're a little bit scattered. So that would be on average a accurate tool, but not repeatable. So we want to make sure that we have repeatable readings within a target.
All right, Dave. For like a torque verification process, is there like a recommended frequency to do this on a power tool, like daily or weekly?
So it's really kind of application dependent and the policies of your company, but obviously a critical type of an assembly may require more frequent checks of the tool, and you can use the process that we showed in setting up a tool the same way to take an analyzer to the tool and then just do a quick verification to make sure that that tool is still performing. We have customers that do that monthly. We have customers that do it weekly. We have customers that are really stringent and they'll actually do those readings before they use the tool. They'll go use the tool, then they'll come back and do readings again, just to make sure that everything is happening correctly. So it's really application dependent.
All right, Dave. I think that's all we had for today.
Awesome. I want to thank you so much for joining us today. If you have any questions, feel free to reach out to us, and we'll be glad to help answer any further questions that you might have. Until next time, thank you very much and have a great day.